Every year, the United States spends more than $40 billion just to repair roads that have already been built, paved, and delivered as finished. This isn't money for building new highways, it's money to patch up what already exists. Potholes open up in the middle of winter. The asphalt cracks under the July sun. Entire stretches of highway, which should last for decades, start to deteriorate within just a few years. And the worst part, it seems that no matter how much is spent, the problem never truly goes away. It's a cycle that every American driver knows and that every American city pays dearly to keep under control. But there is one state that, quietly, has found a way to break this cycle. A place where roads simply last longer, break less, and require less maintenance than anywhere else in the country. And now, transportation engineers from dozens of other states are studying, traveling to, and copying what was done there. That state is Texas, and what happened there may be about to change the way roads are built across America. To understand why this story matters, you first need to understand the scale of the problem in the United States as a whole. The country has one of the largest road networks on the planet, with millions of kilometers of highways, avenues, and rural roads connecting cities, ports, factories, and farms. This network is the circulatory system of the American economy. Virtually everything that is produced, sold, or transported passes at some point along a road. The problem is that much of this infrastructure was built decades ago, at a time when traffic volume, truck weights, and weather conditions were very different from today. Many highways that now handle thousands of heavy trucks per day were originally designed for much lighter traffic. The result is accelerated wear, potholes that multiply faster than repair crews can fix them, and a maintenance budget that grows year after year but never seems to be enough. In addition, there is the climate factor. In the northern states, the freeze-thaw cycle is one of the pavement's greatest enemies. Water seeps into small cracks, freezes, expands, and breaks the asphalt from within. In the southern states, the problem is the opposite. Extreme heat softens the asphalt, causing it to deform under the weight of heavy vehicles, creating ruts and waves in the road surface. In both cases, the end result is the same: pavement that deteriorates prematurely, requiring constant repairs, lane closures, and of course, ever-increasing public spending. For the average driver, this translates into frequent traffic jams caused by roadwork, unexpected detours, and a constant feeling that the road is never truly finished. For a long time, this seemed to be a problem with no real solution. Each state tried in its own way to patch things up, repave critical stretches, and simply live with the problem. But there were few examples of a state that had actually managed to consistently and on a large scale reduce this cycle. That was until the eyes of transportation engineering began to turn toward Texas. The reason why Texas became such an important case study is no coincidence. If there is one place in the United States where roads should deteriorate quickly, that place is Texas. The state has more than 300,000 miles of highways, the largest road network of any American state, crossing arid deserts, vast plains, coastal regions prone to hurricanes, and densely populated urban areas like Houston, Dallas, and San Antonio. This means that Texas pavement has to withstand virtually every possible climate extreme within a single state. Summers that exceed 40 degrees Celsius, sudden cold snaps in winter, tropical storms and hurricanes on the Gulf Coast, and prolonged droughts that dry out the soil beneath the asphalt. Add to that one of the heaviest truck traffics in the country, a result of the trade routes that connect the United States to Mexico through several land borders in Texas. And you have in practice the worst possible scenario for any highway. If a construction method works in Texas, it would probably work almost anywhere in the United States. And it was precisely this hostile scenario that forced the Texas Department of Transportation to innovate. Instead of continuing to apply the same traditional techniques and simply increasing the maintenance budget each year, Texan engineers began, over the past few years, to combine a series of technologies and practices that, together, have profoundly changed the way the state builds and maintains its roads. It's not about a single miraculous invention, but rather a set of solutions that reinforce each other. The first of these technologies is the use of polymer-modified asphalt. Unlike conventional asphalt, which becomes brittle in the cold and soft in the heat, modified asphalt receives polymer additives that increase its elasticity. This means that the material can expand and contract according to the temperature without cracking and, at the same time, better resist deformation caused by the weight of heavy trucks. In practice, it's like replacing a rigid material with another that absorbs stress instead of simply breaking under pressure. This type of asphalt costs a bit more to apply initially, but its lifespan is significantly longer, which reduces the need for constant repaving. The second technology is high-strength concrete, mainly used in critical sections such as bridges, overpasses, and areas with heavy truck traffic. This type of concrete is formulated to withstand much heavier loads and repeated cycles of compression, without developing the typical cracks found in conventional concrete. On highways where the volume of trucks is extremely high, such as the major Texan logistics corridors, this material has proven capable of withstanding decades of intense use with much less maintenance than expected. The third piece of this puzzle is monitoring with sensors. In several highway sections, Texas began installing sensors beneath the pavement itself, capable of detecting variations in pressure, temperature, and even microcracks, long before they become potholes visible to the naked eye. This data is sent in real time to monitoring centers, allowing engineers to identify risk points and schedule preventive repairs exactly where and when they are needed, instead of waiting for the average driver to discover the problem by driving over a pothole. The fourth technology is a modern drainage system. One of the main culprits in pavement deterioration is water that seeps under the asphalt and accumulates there, weakening the roadbed until it gives way under the weight of traffic. Texas began to heavily invest in more efficient drainage systems, with underground channels and permeable materials that direct water away from the road structure, preventing this silent weakening that, in many other states, is the real cause behind much of the potholes that appear after heavy rains. The fifth practice is the use of recycled materials in the construction and repaving of highways. Crushed asphalt, originating from old sections that have been removed, is reprocessed and reused in new paving layers. In addition to significantly reducing costs, this process also decreases the amount of discarded material and, in many cases, recycled asphalt, when combined with the right additives, performs as well as or even better than completely new materials. And the sixth piece, perhaps the most important of all, is a change in mindset: preventive planning. Instead of waiting for a road to fail before taking action, Texas began to adopt a scheduled maintenance system in which small interventions are carried out regularly, long before the problem becomes visible. This may seem like a simple detail, but in practice it represents a radical change in the way a Department of Transportation operates. Instead of a reactive system that is always trying to catch up, a proactive system is created, one that anticipates wear and tear and acts before it affects drivers. When these six pieces are combined, the results start to appear consistently. Sections of highway that began to receive this set of technologies recorded a significant reduction in the number of potholes formed each year. The need for emergency repairs, those that suddenly close lanes and create unexpected traffic jams, also dropped significantly in these sections. It is estimated that, over time, these practices have generated savings on the order of billions of dollars for Texas's public coffers, simply because the money that would have been spent on constant repairs began to be invested more efficiently, preventing problems from getting worse. The average lifespan of the pavement in these sections increased considerably, which means fewer construction works, fewer closures, and less inconvenience for those who rely on these highways every day. And, as a direct consequence, there was also a reduction in traffic jams caused by maintenance work, since fewer emergency repairs mean fewer lanes being closed at the last minute. Faced with results like these, it didn't take long for other states to start paying attention. After all, if a state with the harshest climate, the heaviest traffic, and the largest road network in the country managed to reduce its deterioration cycle, why couldn't other states do the same? Florida was one of the first to draw inspiration from the Texas model, adapting the technologies to deal with its main challenge, hurricanes and heavy rainfall. Florida's engineers began investing in drainage systems similar to those in Texas and in materials more resistant to constant moisture. A natural adaptation, considering that much of the state is exposed to recurring tropical storms. Arizona, in turn, found in the Texas model an answer to a problem very similar to its own: the extreme desert heat. Sections of highway in Arizona began to receive polymer-modified asphalt, following exactly the same logic applied in Texas to prevent pavement deformation under extremely high temperatures. Georgia and North Carolina launched pilot projects directly inspired by Texan practices, testing the use of monitoring sensors on high-traffic stretches, aiming to anticipate problems before they became visible to drivers. And Virginia, a state with a large volume of truck traffic along the East Coast, also began studying the adoption of high-strength concrete at critical points in its road network, following the example of Texas's logistics corridors. What began as a regional response to a specific problem in Texas gradually turned into a model that is now being replicated in various parts of the country. And when you place these two groups of states side by side, the difference is visible even to those who know nothing about civil engineering. On one side, you have stretches of highway built with these modern technologies, featuring smooth surfaces and few visible cracks even after years of heavy truck use. On the other side, there are stretches that still follow traditional methods, with worn pavement, visible patches, recurring potholes, and a constant cycle of emergency repairs that never seems to end. It's practically the portrait of two different eras of road engineering, coexisting at the same time within the same country. And what's most interesting is that this story seems to be just beginning. What comes next could represent an even greater leap than everything that has been done so far. Engineers are already testing artificial intelligence systems capable of analyzing data from sensors spread over kilometers of highway and predicting months in advance exactly where and when a stretch of pavement will begin to fail. This would allow maintenance teams to act even before any visible signs of wear appear, making the preventive maintenance system even more precise than it is today. Prototypes of smart asphalt are also being developed, capable of reacting to sudden temperature changes by automatically adjusting its rigidity to prevent both cracking in the cold and deformation in the heat. Another technology under development is self-healing concrete, a material that contains microcapsules with sealing agents that break open when a small crack forms, releasing a compound that fills the fissure before it becomes a bigger problem. And on an even larger scale, the use of satellite monitoring is starting to gain traction, making it possible to map the wear and tear of entire highways in real time. This allows transportation departments to have a complete overview of the condition of their roads without the need for constant manual inspections. If this set of technologies continues to advance and be adopted on an increasingly larger scale, it is possible that, a few years from now, we will look back and see Texas not only as the state that solved its own infrastructure problem, but as the place where a new national standard for highway construction in the United States was born. A state that has always been known for its size, its relentless heat, and its vast distances may also end up being remembered for having found the answer to a problem the entire country had faced for decades: how to build roads that truly last.